In this video, we will explore IoT communication protocols with Contiki operating system and focus on the practical demonstration of key IoT protocols 6LoWPAN, RPL, and CoAP. But before we dive into the practical implementation of these protocols, let us first understand Contiki OS and its exceptional features. Contiki is an open source operating system for the Internet of Things which connects low-cost, low-power microcontrollers to the Internet. It was developed by a Swedish computer scientist, Adam Dunkels, in 2002. While the development of the original Contiki OS started as early as 2002, it was officially open sourced in 2006, transforming it into a community-driven project. The primary goal of developing Contiki was to provide a lightweight, flexible operating system tailored for resource-constrained IoT devices. The original Contiki OS has a modular architecture and provides an event-driven kernel. While offering support for IPv6 and low-power modes, the original Contiki exhibits certain limitations in terms of security features and extended support for RPL protocol. And thus, as technology evolved and new requirements emerged, the need for an enhanced version became evident. This led to the development of Contiki-NG, where NG stands for Next Generation, and it is a new enhanced version of the original Contiki OS. Contiki-NG is an open-source, cross-platform operating system for next-generation IoT devices. It provides an RFC-compliant, low-power IPv6 communication stack enabling Internet connectivity. It focuses on dependable, secure, and reliable low-power communication and standard protocols such as IPv6, 6LoWPAN, RPL, and CoAP. The system runs on a variety of platforms based on energy-efficient architectures such as the ARM Cortex-M3 and the Texas Instruments MSP430. The code footprint is of the order of 100 kilobytes and the memory usage can be configured to be as low as 10 kilobytes. The source code of Contiki-NG is available as open source and comes with the extensive documentation, tutorials, a roadmap, release cycle, and a well-defined development flow. Now let us look at some of the key features of the Contiki operating system. First is the modular architecture. Contiki's architecture is organized as components encapsulating a specific functionality, and the code base is also divided into small, independent modules, each responsible for a specific task. These modules can be developed, tested, and maintained separately, making it easier for developers to understand, modify, or extend specific functionalities without affecting the entire system. Next is the programming model. The programming model of Contiki is event-driven, where the execution of tasks is triggered by events. Contiki employs cooperative multitasking, where tasks voluntarily yield control to the operating system. Unlike preemptive multitasking, where the OS forcibly switches between tasks, cooperative multitasking relies on tasks releasing control when they reach a yield point. This approach is well suited for resource-constrained IoT devices as it reduces the overhead associated with task switching. Processes in Contiki are implemented using proto-threads, which are a form of lightweight, stackless threads that simplify the development of event-driven code. Also, the Contiki programming language uses C syntax for writing programs which are compiled using the GCC compiler. In terms of the platform and hardware support, Contiki provides hardware abstractions that encapsulate hardware complexity. This approach makes Contiki versatile, enabling support for a wide range of hardware platforms, which allows developers to use the OS across diverse IoT devices without major modifications. Last key feature is the simulator support. Contiki also provides a simulator named Cooja, a network simulator that combines low-level and high-level simulation of IoT devices and networks. It is a powerful tool used for testing and debugging IoT applications in a virtual environment before deploying them on a physical hardware. Cooja allows cross-level simulation, which means it provides simulation support at many levels of the system. It is written in C and Java, which makes it user-friendly simulator. One of the main advantages of Cooja is that apart from providing features for simulation, it also supports certain features associated with device emulation. Cooja emulates the behavior of individual nodes or devices in a network. It simulates their responses to events such as incoming data or timer expirations, providing a high-level representation of device behavior. Now let us understand how to install and set up the Contiki operating system. Depending on the requirement and target platforms, there are multiple ways to install Contiki. Cloning the Contiki repository from GitHub or downloading it from the official release page. The second could be using the Contiki Docker images. The third could be through the Instant Contiki VM, which is a virtual machine image created with all necessary toolchains and software for Contiki OS development. In this video, we will proceed with the easiest way of installing and using Contiki OS, which is by using Instant Contiki. This option of installation is quick, easy, and avoids the manual installation steps and dependencies. These are the steps to download Instant Contiki. First step is to download VirtualBox. Then in the second step, you download Instant Contiki virtual image. In the third step, create a new virtual machine with the VirtualBox. And then you choose Linux, follow some basic steps, and in hard drive, choose the existing virtual hard drive. Inside the Instant Contiki, select the VMDK file that does not have the -S00 star trailing, and then create the virtual machine. After creating the virtual machine, you can use the password as user to continue using Contiki operating system. Now we will look at the practical demonstration of Contiki operating system. So this is the user interface of Contiki operating system, wherein you have by default the terminal application available on the desktop. When you go to the places option on the menu, you go to the home folder to actually see where the Contiki was installed within your virtual machine. When we click on Contiki, here we have multiple folders which indicate how the device is going to communicate amongst themselves as well as with devices on the internet. As with any other operating system, we have files related to the core operations of the system. We also have some files within the CPU which relates to the processing capabilities of the IoT device. We do have examples folder to help the user run by default applications within Contiki. So as we discussed, we had a Cooja simulator within Contiki operating system, and to run the Cooja simulator within Contiki, we have to open the terminal application. Once we open the terminal application within Contiki, we have to go to the specified path, and the specified path is we go to Contiki, Tools, and we go to Cooja. So the Cooja simulator is actually present within the Tools subdirectory of the Contiki operating system. And as we have gone to the specified path, we write the command ant run, that is ant run, to actually run the Cooja simulator. Once we have done this, the operating system is going to execute the Cooja simulator. Certain commands will be executed, and by default, the Cooja simulator will pop up in front of you. So this is actually the graphical user interface of Cooja, which is the Contiki network simulator. And as you can see, we have certain options in the menu bar which include the file, simulation, modes, tools, settings, and help. As you can see, in the file option, we have the option of new simulation, and when we click on new simulation, there will be certain advanced settings that will come up in front of you, and here you can set the name of the simulation. You can also set the radio medium that you want within your IoT environment, which is going to determine the radio surroundings behavior. You can also set up certain amount of delay within your mode startups. Then there will be a random seed which will help you to control the random behavior such as mode startup delays, node positions, etc. And then whether you want to have a new random seed on each reload, you can actually click on this icon. So let us say I am naming my simulation as test simulation. And then I click on create. So once I click on create, you will have a number of windows that will come up in front of you, which includes the network window. This window will actually include all the sensor modes which are available in your IoT network. We have the simulation control window from where you can actually start, pause or reload your simulation. The notes window is actually for you to keep some notes within your simulation. The mode output will show all the output that the sensor modes are actually displaying. In the timeline window, we will actually see the behavior of various sensor modes, which include their transmissions, their receptions, as well as when they are in the idle mode. So these are the 4-5 windows that will come up in front of you. So let us start and build a basic Hello World program in the Contiki operating system. So while developing programs for Contiki operating system, we have two options. The first option is either you use the terminal window and develop programs, or the second option is you use the Cooja simulator. So first we will discuss the terminal option, wherein we will go to a new terminal, right? And we will move out of this path, and then we go to a path where all your examples are there. So we write down CD Contiki, and then we write examples. And if we want to list all the examples that are there, we just write ls, which is going to list all the examples that are available in this folder. And then when you want to go to the first program that we are going to run is the Hello World program within the terminal. So what we do is we just go to Hello World, CD Hello World. So once we are in the Hello World directory, to run the Hello World program from the terminal, we just write make Hello World. This will actually compile the C program which is already there in the examples folder. And by the time it is compiling that program, we can actually have a look at that Hello World file which is there in the examples folder, and we go to this Hello World option. In this Hello World folder, we have the hello world.c file, and as we discussed, Contiki has a programming, all the programming in Contiki is in C. Basically, this is a very simple Contiki application which shows how the Contiki programs look. So as you can see, just like all other C programs, the first two lines are wherein we are trying to include the header files, which is the Contiki.h and the device leds.h. Then we also have another header file which says #include stdio.h, which is for standard input output. Then we have two lines which says process and auto start process. As we discussed in Contiki, we have processes, and through these lines we are actually trying to create a process, Hello World process, with the name as Hello World. And then with the line auto start processes, we are actually giving the address of that process to initiate the process whenever the mode is up. Then with process underscore thread, we are actually trying to start a process and set up a timer that expires after 10 seconds through the line e-timer underscore set. And then while 1, we are actually trying to print Hello World just like in any another C program. And then we are ending the process with the line process underscore end. As you can see, while we were discussing this program Hello World.c, the program is also compiled on the terminal. Now to actually see the output, what we have to do is we write /hello world.native. Now this output is actually showing you all the output which will be displayed on the sensor mode if you were deploying this particular Hello World program on a sensor mode. And if you closely observe the output, we have static Contiki-NG. Then for routing, it says it is using RPL Lite, which we will actually see in the next video, how to implement RPL on Contiki. Then for net, it is using TUN6 for connectivity with the internet. And as you know, for the on the Mac and the physical layer, we have 802.15.4 in IoT for standardized communication. And then we have the link layer address and the tentative link local IPv6 address of this particular mode. And as you can see, continuously the mode is printing Hello World. It will continue to do so until we are actually stopping this process. So this was one method wherein you can actually implement the Hello World program from the terminal. Now let us see how you can actually implement this Hello World program from the Cooja simulator. So to run the Hello World program from Cooja simulator, we need to open the Cooja simulator, and the commands are the same, that you go to the cd Contiki tools Cooja folder and then you just write and run. Once you do that, after running certain commands, Cooja simulator will pop up in front of you, and as discussed, to initiate a new simulation, we go to File and then click on New Simulation. Herein we write the simulation name and set other parameters that you want for the simulation. Since this is only to deploy the Hello World application, we will not change any of the advanced settings. Once we click on Create, we will have all the windows. Then to actually add a mode to the network, we just go to the modes option, which is the third option in the menu bar, and click on Add Modes. Then click on Create New Mode Type, and therein we have a number of mode types. You can use any of the mode type. For this example, we are actually going with the Z1 mode, that is the Zolertia mode. Once you click on the Z1 mode, the description will show you the name of the mode, and then herein you have the second option is Contiki process or firmware, which is the file that you actually want to upload in this particular Zolertia mode. So you click on Browse, and then you go to the home path in Contiki. You go to Examples. In Examples, we actually want to upload the hello world.c file in this mode within Cooja simulator. We click on Hello World, and then in Hello World, we choose the option hello world.c, and then we click on Open. Once we click on Open, we just click on Compile. So this the other option, which is the clean option, is actually to remove the previous compilations or the object files if there are any in the hello folder. So we just click on Clean once. This will actually remove all the previous object files of the hello world, and then we click on Compile. If you observe carefully, each of the files which are within the operating system will be compiled one by one, as you can see in the compilation output. As the mode is getting compiled with the hello world.c, and once it is compiled, this create button will be enabled. As you can see, again, as was in the case of the terminal, we have the hello world.co, which is the object file of the hello world, and then you click on create. Once we click on create, we just want to tell how many these type of modes we actually want in our networks. So assuming we want such 5 modes in our networks, we just type 5 and click on add modes. As you can see, as we click on add modes, 5 modes will come up in the network window, and if we zoom in the network, we can actually see all these modes present in the network. And then within this network window, we have 2 options in the menu. One is the view and another is the zoom. In the view, we can actually click on mode type. Once we click on mode type, since all these modes are having the hello world program, or they are actually running the hello world program, all will be colored with all will have the same color, that is green. So now you want to start the simulation, and to start the simulation, you go to the simulation control window and you click on start. Once we click on start, in the mode output, we will see one by one all the modes, that is the 5 modes that you have considered in your network. They will actually start up, and once they start up, each of the protocols, which is like the MAC protocol, that is the IEEE 802.15.4, or it is the IPv6 protocol, they all will start initiating within each of the modes, and then the process that you actually created, that is the hello world process, will start running on these modes. And this will be the same for all the modes, that is all the 5 modes. And once they have done it, as you can see, it says starting hello world process, and then whatever message that you have displayed will come up in the mode output. Now let us actually go and observe the code wherein this output is being actually we are displaying this output within the code. So we pause the simulation, we go back to our home folder. Within examples, we go to hello world. And as you can see, in this hello world.c file, we are actually printing sensor says, and then we are actually printing a count. That is why the output was different compared to the one which we did in the terminal window. We can actually change this output, and we can actually modify it to printf hello world, or in fact we can just write welcome to IoT. welcome to IoT, right? Like this, we can change the C file and we can save the file using Control S. Once we have saved the file, we go back to our simulation in Cooja and we click on reload. By clicking on reload, we will be recompiling the C file within the Cooja simulator, and then once we click on start, as you can see, the mode now the mode output will actually display welcome to IoT, right? Like ID2, that is the sensor mode 2, is actually displaying welcome to IoT. Likewise, ID4, that is mode number 4, is also displaying welcome to IoT. So this was the basic first program that you can run within the Contiki operating system either using the terminal window or using the Cooja simulator. In this video, we explored the architecture and programming model of Contiki, wrote some basic Contiki programs, and got a glimpse into the powerful Cooja simulator. In the next video, we will look at the implementation of standardized IoT protocols in Contiki OS and their simulation in Cooja Network Simulator. Thank you.